Okay, let's dive right into this. I want you to picture something for a second. Imagine your upcoming Cambridge physics exam hall isn't just a room with desks, but an actual high-stakes Formula One racetrack. You've got extremely limited time, you've got immense, heavy pressure weighing on your shoulders, and honestly, every single second, every single mark absolutely counts. Now think about it like this. You can have the absolute most powerful, fine-tuned engine in the world. And by that, I mean you know all the physics facts. You've memorized the textbook, you know the theories inside out. But if your pit crew strategy is fundamentally flawed, if your tires aren't being changed efficiently, you are going to lose the race. It's that simple. Today, we are exploring a comprehensive strategic framework that is completely designed to overhaul your entire approach to Cambridge IGCSE Physics. Whether you are currently sitting in the classic syllabus 0625, or maybe you're tackling the equivalents like 0651, 0652, or 5054, or hey, maybe you're even setting your foundational groundwork for AS Level 9702. This explainer absolutely applies to you. We are going to be looking at the core, fundamental physics concepts of motion, speed, and velocity. But we're not just going to read textbook definitions. We are analyzing them strictly through the lens of a top-tier racing strategist. We're applying literal pit crew efficiency to your exam timing, because every single second counts and every single mark needs to be systematically, ruthlessly secured.
So right off the bat, we have to ask a massive question. Why do candidates consistently crash and burn on simple motion equations? I mean, you'd think kinematics is pretty straightforward, right? It's literally the first thing you learn in the syllabus. But let me introduce you to two archetypical students I see all the time in the past paper trenches. Let's call them Alex and Sam. First up, we have Alex. Alex is our walking, talking encyclopedia. If you were looking at a dynamic split screen of their past papers right now, you would see Alex completely overloading their answer sheet with raw physics facts. If a question asked to, say, describe a car's motion, Alex goes rogue and writes a literal novel about the history of the equation V equals S over T. They're dumping every single equation they've ever memorized onto the page, but they are providing absolutely zero analytical application to the specific car mentioned in the question. Then, on the flip side, we have Sam. Now, Sam understands the physics, sure, but Sam is terrified of the timer. Sam is racing against the clock and letting the pressure win. Sam rushes, barely even glances at the command words in the prompt, sees the word velocity jumping out, and just carelessly drops a basic generic definition for speed, completely missing the crucial, specific requirements of the question. If you put their papers side by side, covered in the examiner's red pen, both of these approaches result in massive, massive dropped marks. The engine is running perfectly, but the steering is totally broken. They are both crashing before the finish line.
Listen to this. This is a direct, verified quote from a senior Cambridge examiner. They state, plainly and clearly, motion is one of the most misunderstood areas in physics. Let's fix that right now. Notice something really important there. They didn't say it's the hardest math. They didn't say it's the most mathematically complex topic. They said it is the most misunderstood. And that misunderstanding, it doesn't come from an inability to divide distance by time. You all know how to do that. The misunderstanding stems from a complete failure to decode what the exam board is actually asking for. When you lose marks here, it's a strategic failure. It is not a knowledge failure. So we are going to fix that right here, right now. We're going to take Alex's frantic info dumping, we're going to take Sam's panicked rushing, and we are going to calibrate both of those extremes into a precision, point-scoring, exam-crushing machine.
To get us there, here is our strategic track map for today's explainer. First, the motion crash course. Second, graph interpretation under pressure. Third, the method mark strategy. Fourth, avoiding generic examiner pitfalls. And finally, number 5, mastering comparative analysis. Let's get right into it. Section 1, the motion crash course, the theoretical architecture of kinematics.
Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's look at the engine. In Cambridge physics, precise definitions and causal relationships are strictly 100% non-negotiable. If your definitions are sloppy, your entire structural foundation just crumbles. Remember, you are being tested on your knowledge with understanding, your ability to handle information, and your problem-solving skills. And you absolutely cannot solve a complex problem if your underlying understanding is vague or wobbly. For instance, let's look at the absolute basics, speed versus velocity. Speed is the distance traveled per unit time. The formula is V equals S over T. It is a scalar quantity. That means it only cares about magnitude, just the number. But velocity? Velocity is speed in a given direction. It is a vector. Missing the directional component of velocity in your answer is an immediate, devastating mark loser. It is literally the equivalent of getting a 10-second penalty in the pit lane because you weren't paying attention. To guarantee top marks, top-tier students structure their descriptive physics answers using the PEAL framework. You need to memorize this. PEAL stands for Point, Evidence, Explanation, and Link. Let me show you how it works. If an examiner asks for the difference between speed and velocity, your point is simply stating that velocity is a vector. Boom! Then your evidence is explaining that it has both magnitude and direction, whereas speed is just a scalar. Next, your explanation gives the deeper physics context, detailing, for example, that an object moving in a perfect circle at a constant speed actually has a constantly changing velocity simply because its direction is constantly changing. And finally, your link ties all of that theory back to the specific scenario in the question, like, say, a satellite orbiting the Earth.
To really see the PEAL framework in action, I want you to imagine a 30-second timer on the clock, right now. We are going to compare two live answers. First, let's look at Alex's totally vague answer. Alex wrote, speed is how fast you go, like v equals s over t. And velocity is basically the same thing, but for physics equations. Okay, wow. Alex is overloaded on raw colloquial facts and entirely missed the core physics point. The examiner looks at that and gives it 0 marks. It's a crash. Now let's look at Sam's highly specific, fully revised answer. Sam wrote, speed is a scalar quantity defining distance traveled per unit time. Velocity is a vector quantity, meaning it represents speed in a specific given direction. Do you see the difference? Sam hits the nail right on the head. Sam didn't just write a bunch of words hoping something sticks. Sam delivered a precise, direction-inclusive velocity definition. This is exactly what examiners are trained to reward. They are scanning your paper for those specific, high-value keywords: scalar, vector, distance per unit time, given direction. When you use the correct syllabus-approved terminology, the examiner's red pen instantly transforms into a green check mark. Your mark potential goes from 0 to 100%.
Section 2. Graph interpretation under pressure. Distance time versus speed time graphs.
Okay, this right here is the next major hurdle where students absolutely hemorrhage marks. Picture it. You are in the exam, the clock is ticking down, your heart is beating fast, and you are faced with a graph. Under pressure, candidates constantly, and I mean constantly, confuse distance time graphs with speed time graphs. You have to extract precise mathematical data from these motion graphs, and if you misidentify the axes in a panic, your entire calculation is totally doomed from the start. This matrix we're looking at is your crucial, life-saving roadmap. Let's walk through it step by step. Look at the top row, the rest state. On a distance time graph, rest is a flat, horizontal line. Why? Because the distance isn't changing as the time ticks on. You're staying in one spot. But over on a speed time graph, rest is a line flat on the x-axis down at absolute 0, because your speed is 0. If you see a horizontal line up high on the y-axis of a speed time graph, that is not rest, that is constant speed. Now look at the middle row, constant speed. On a distance time graph, this is a perfectly straight upward diagonal line. The gradient, or the slope of that line, actually equals the speed. But jump over to the speed time graph, and constant speed is a flat horizontal line hovering above the x-axis. Finally, let's look at acceleration. On a distance time graph, acceleration is an upward swooping curve. The gradient is getting steeper and steeper because the speed is actively increasing. But on a speed time graph, constant acceleration is a straight diagonal line going up where the gradient equals the acceleration and, crucially, the area under that graph equals the total distance traveled. Imagine I gave you a 60-second interactive challenge right now to rewrite a flawed graph interpretation. If you don't know this exact matrix by heart, you will inevitably calculate the gradient of a speed time graph and accidentally call it speed instead of acceleration, and you will lose all the marks.
This brings us to a massive, screaming examiner alert. Seriously, pay attention to this. Candidates referencing cross-topic connections achieve significantly higher marks. What does that actually mean for you? It means the syllabus explicitly mandates that top-performing students must exhibit connected conceptual understanding that transfers seamlessly to unfamiliar contexts. Examiners want to see that your brain isn't just a filing cabinet of isolated facts. For example, if you are looking at a speed time graph showing a parachutist jumping out of a plane and eventually reaching terminal velocity, which is where the curve slowly flattens out into a horizontal line, don't just lazily say acceleration decreases to 0. That's too basic. Connect it. Mention that the upward air resistance has steadily increased to perfectly balance the downward weight of the parachutist, meaning the resultant force is now exactly 0, and which, according to Newton's second law, F equals ma, means acceleration must also be 0. When you connect kinematics to forces like that, you are actively signaling to the examiner that you have a comprehensive, master-level grasp of the material. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, moving into Section 3, the Method Mark Strategy, the pit stop procedural framework.
Think back to our Formula One pit stop metaphor. In a real race, those mechanics don't just run around wildly hoping the tires get changed. They have a highly specific, flawlessly synchronized step-by-step process. The exact same logic applies to your physics calculations. In Cambridge exams, marks are heavily awarded for the process, not just the final magical answer. If you just magically write down a final number and it happens to be wrong, you get 0, nothing. But if you clearly show the process and just make a tiny, silly calculator error at the very end, you might still get 3 out of 4 marks. That's what we call method marks. Principal examiners expect to see these 5 infallible steps applied to every single complex problem. Step 1, deconstruct the question. You need to decode the command words. Are they asking you to calculate, determine, describe, or explain? Describe means simply state what happens. Explain means you must state why it happens. Step 2, extract relevant data. Pull the raw numbers out of the dense text and write them down clearly with their units. Say to yourself, okay, V equals 15 meters per second, T equals 30 seconds, and always check if the units need converting. Step 3, select the analytical framework. Write down the blank formula before you put numbers into it. Write A equals V minus U all over T. Doing this alone often magically secures a method mark. Step 4, execute with clear notation. Substitute your extracted numbers in clearly so the examiner can follow your logic. Step 5, present with correct terminology. Write the final answer with the appropriate significant figures and the absolutely correct unit. Leaving the unit off your final answer is exactly like a pit crew putting a new tire on a car without screwing in the bolts. It's a disaster.
To really put this into practice, the official examiner guidance states that we must, and I quote, extract from texts and tables, interpret relationships, and draw evidence-based conclusions. So let's run a quick interactive workshop. Challenge 1, the data scan. Imagine a complex physics data table pops up on your exam, showing the braking distance of a car at various different speeds. Imagine a 60-second visual countdown timer ticking away. Your job in that 60 seconds isn't to read and memorize every single random number. Your job is to extract the core underlying trend. You must interpret the relationship. Ask yourself, as the speed of the car doubles, does the braking distance also just double? No, it quadruples. Why? Because kinetic energy is half mv squared. The velocity is squared. And remember, strict conventions are absolutely critical when executing this framework. You need proper headings, appropriate formats, and crystal clear annotations. If the exam asks you to draw a graph, you better use a sharp pencil, make sure your plotted points take up more than half the provided grid page, and definitively label your axes with the correct units. Evidence-based conclusions require actual evidence, so make sure you are actively quoting the raw data directly from the table in your written paragraph. Show them you know how to use the data.
Section 4, Avoiding Generic Examiner Pitfalls. The top 3 application errors.
All right, so we've spent time looking at what you should do, but let's sharply shift our focus to the specific glaring warnings pulled directly from the Cambridge Principal Examiner reports. These are the brutal traps that cost perfectly smart students their top grades year after agonizing year. Let's do Challenge 2, Find the Flaw. I'm going to read a sample student paragraph, and I want you to spot exactly where the marks are being lost based on these top 3 errors. Here's the flawed paragraph. The object accelerates because there is a force on it. Then it goes at a steady speed. The graph shows it going up. Okay, let's bring in the examiner commentary. Where are the fatal flaws? First bullet point, it's way too vague. They wrote the object instead of specifying the rocket or the car. They wrote a force instead of defining it as an unbalanced forward thrust. Second bullet point, presentation conventions. Saying the graph shows it going up is terrible, informal terminology. We are physicists. We should say the speed-time graph exhibits a positive constant gradient. Third bullet point, context. They didn't relate any of this to the specific scenario provided in the exam prompt. Students hemorrhage so many marks due to these easily avoidable formatting and contextual errors. You must be precise.
Which brings us to this critical examiner alert. Burn this into your brain. The classic mistake is providing generic answers. Context is king. Always link every single point back to the given scenario. This is a high-impact memory hack that will save your grade. Generic, copy-pasted textbook answers will never secure top marks, no matter how much raw, beautiful physics knowledge you display. Let's do Challenge 3, Speed Writing.
Imagine you have a 30-second timer to write one perfect peel paragraph explaining why a heavy delivery truck takes longer to stop than a lightweight bicycle. You don't just blindly write F equals ma and hope for the best. You specify the context. You write. The delivery truck has a significantly larger mass than the bicycle. That's your point. Therefore, for the exact same given maximum braking force, the deceleration of the truck will be much smaller, according to the formula, A equals F over m. That is your evidence and explanation working together perfectly. Consequently, if both are traveling at the same initial velocity, the heavier truck requires a significantly longer stopping distance. And that right there is your link to the context. That is a perfectly meticulously executed paragraph that leaves the examiner absolutely no choice but to award you full maximum marks.
Section 5. Mastering Comparative Analysis. Crossing the finish line into the top tiers.
When those really tough, high-mark questions ask you to compare or evaluate, the examiner is actively testing your highest-level cognitive skills. Top-scoring candidates don't just guess here. They systematically build comparative arguments using this exact evidence-based criteria. Let me present to you the final complete physics answering system. Think of this as your cheat sheet recap. These are the 3 rules that absolutely guarantee top marks when you are doing complex analysis. Rule 1. Command word decoding. If the command word specifically says compare, you must identify similarities and differences. If you just write down a list of differences, you automatically lose half the marks immediately. Rule 2. Peel framework application. You need to use comparative connectives to guide the examiner's eye. Words like whereas, however, or conversely. For instance, car A has a constant acceleration, whereas car B's acceleration is continuously decreasing. Then you must support each of those comparisons with hard evidence pulled directly from the graph or the data table provided. Rule 3. The time management matrix. Do not, under any circumstances, spend 10 minutes agonizing over a 2-mark comparison question. Use your F1 pit stop strategy. Draw your conclusions about relative importance quickly and concisely. Ask yourself, which factor has a bigger impact on kinetic energy, doubling the mass or doubling the speed? Well, doubling the speed because velocity is squared in the formula half mv squared. State it clearly, prove it mathematically, and move on to the next lap.
Ultimately, a successful candidate must demonstrate deep, evaluative thinking by questioning assumptions, considering different perspectives, and rigorously justifying their decisions with evidence. The absolute best answers justify every single analytical step. For instance, if you assume air resistance is negligible to make your calculation work, write that assumption down on the paper. Say, assuming air resistance is negligible, the acceleration of freefall is a constant 9.8 meters per second squared. Doing this shows the examiner that you truly understand the real-world limitations of the theoretical physics models you were using. You aren't just a calculator, you are a physicist. Now, students who implement these exact physics strategies see an average improvement of 2 full-grade boundaries. But, and this is a big but, that only happens if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @AceTheExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @AceTheExams_IGCSE and click that bell. Don't let another exam pass you by.
So I want to leave you with this final, provocative thought to chew on before your next test. Will your next exam answer be a generic, rushed crash into the barriers? Or will it be a meticulously executed, high-speed victory lap? You now have the exact blueprint. You know how to decode those tricky command words. You know how to flawlessly apply the PEL framework. And you know how to execute your time management strategy like an elite F1 pit crew. The track is fully yours to conquer. Drop a comment below with your target grade for physics and the biggest challenge you're currently facing. Our team responds to every single comment. Like and share this video with a study partner who needs to hear this. Ace the Exams. Your Cambridge success starts here.